Hello everybody, Zach Ludwigson here. I'm going to talk about my, what's this thing called? The problem assignment video, that's what it is. A little bit about the course that this will be involved in. Is the IBHLAA math class. So this is considered analysis and approaches high level, IB. So I've got 25 students in the class, one ninth grader who's 2 years accelerated, 4 10th graders that are 1 year accelerated, 13 11th graders that are kind of right on, and then 7 12th graders that are in the class. About half the class is calculus based and half the class is kind of a bunch of scattered topics. The group in general is really a highly motivated class, very interested in challenge type questions and anything that involves kind of some mental fortitude along the way. So quite a few of them have said that they're pursuing or want to pursue a degree in either math or engineering. That's obviously to be determined, but at this point that's what they're saying. Whether that's to impress me or not, or just to kind of look a certain way in front of their peers, I don't know, but that's what they say. And again, like this course in general is pretty heavy in this idea of problem solving techniques and strategies that some of which we've been looking at in our course here through MSUM. So course content that this particular document on the lesson is related to is actually, I wrote this and it's not what I intended. I was originally intending a related rates problem, but this is actually a closely related but an optimization problem, which kind of lends to this idea of problem solving in a really good way. So the first and kind of main objective that I'd like students to get out of this particular lesson is that they'll be able to understand, again, this should be optimization, but come up with a plan, work their plan, and one thing that I emphasize heavily is sketching and kind of finding an equation that relates appropriate variables, and then of course finding a solution to the problem. In this particular example, students are required to have really, really basic physics knowledge. So one thing that I, in the past, did not address directly and just kind of let happen naturally in the process was, we just talked about the basic concept of speed being distance over time. And we'll see that come up here in the example in the following slide. So let's take a look at the example. So here's the example, and I can read aloud and then kind of talk through what I'm hoping that students will kind of get out of this problem. So Tom is on a rowboat 2 kilometers from a straight shoreline. 6 kilometers from the point on the shore closest to Tom is a town. Tom wants to travel to the town as quickly as he can. If he can row at a speed of 2 kilometers per hour and jog at a speed of 5 kilometers per hour, how far down the shore should Tom dock his boat so he minimizes his time of travel? So one of the first things that, when we talk about problem solving, we talk about, kind of the first stage of Polya's process, which is understand the problem. Okay, switch from highlighter, there we go. Understand the problem. And in this stage, really what I'd like them to be doing is kind of being able to sketch and then assign variables. In this particular video, I'm going to sketch and kind of formulate the equation, but I'm not going further than that. So here's Tom's boat. And the shoreline doesn't matter if it's to the left or right of the boat, so it doesn't really matter. I'll put it over here to the left. And we know this distance here is 2 kilometers. And then from the point closest to the boat on the shoreline, not to scale, is this town. And that town is 6 kilometers down the shoreline. So I'd like them to be able to at least, kind of get something on paper, sketch something and understand kind of the orientation of the problem itself. From there, they have to connect some variables. So when it comes to the different speeds, right? So the speed at which Tom can travel on the water is 2 clicks per hour, and the speed at which he can jog or land travel would be 5 kilometers per hour. So what I'd like to see them do is kind of define those, right? So maybe dw dt, right? So travel along the water, or change in water travel with respect to time, we would have a 2 kilometers per hour. And then maybe dl dt, or travel on land with respect to time, would be 5 kilometers per hour. Okay, so here comes the hard part, and this is the toughest part, right? So now they can at least see the problem, right? So they can see like what they're trying to do. Well, if we just row straight to shore and then jog straight to the town, clearly that's not going to be our minimum time for Tom. So we gotta come up with a plan, right? Come up with a way for us to kind of model this using maybe some calculus reasoning. So my dogs are in the background, so if you hear that, I apologize. So I like to direct them, and this takes some some techniques we talked about earlier with regards to that second part of the process, which is to formulate a plan, right? So let's come up with a plan. Well, in order to have a plan, right, we gotta have some variables involved. So what I like to do is within the problem itself is to give them some leading questions, right? Kind of direct them without giving them the answer. I like to have them, in this particular example, identify like this question here: how far down the shore should Tom dock his boat? Right? Let's say this is our optimal location. Well, then let's call that our variable. Let's call it x, right? So what we want to do is we want to come up with a time function with respect to x, and then optimize that time function. All right, so clearly then some things arise, so I can lead them without telling them directly, like, hey, there's a triangle that we have present here, right? You can see that triangle right here. How can we relate the 3 sides? Because clearly the boat, Tom would be sailing along this distance here. This is a distance, so using Pythagorean theorem, we can come up with that distance. And then, well, what would remain? What distance would we have left? Would be this. So essentially, our distance traveled with respect to x would be, the sum of these 2 functions. So the hard part for me, and it has been for a long time, is to just not give them too much. All right, so, and of course that yellow distance would be 6 minus x. So to not give them too much, but to kind of help, have these leading questions that can allow them to formulate their own ideas. So this is kind of where I leave them standing, right? So here's your plan, right? Let's minimize this function t of x, but they have to come up with t of x. And this is probably the hardest part for them, kind of that, bridging this gap is the toughest part. But this is when the physics comes into play, right? So, or maybe this isn't even considered physics, I don't know, it's really basic, but if speed is distance over time, then time is distance over speed. Well, I know distance. Here are my 2 distance functions, so to speak. So if I took distance and divided by speed for those particular modes of travel, well, the speed for water travel we had 2, and our speed for land travel was 5. So I would have 6 minus x divided by 5. And now we've got t of x. And of course, from there, there's some calculus involved to find t prime, set it equal to 0, and then find the x value for which that's a minimum. Now, this is a great time for me to kind of bring up resources for them, right? When we minimize or maximize a function, right? We're talking first derivative, second derivative test. So these are great opportunities for them to utilize prior knowledge in the process. So with regards to finishing up kind of problem solving methods, right? So they would execute their plan, and then of course kind of look back at their process and their solution and see if it makes sense. So in this particular example, it's interesting that t prime equals 0 at a positive value. I don't recall exactly what it was, and also a negative value. So, there's some reasoning to be done here, right? They look at these two values and they just have to take the context of the problem and make sure that it makes sense. So clearly, we would not want a negative value for x, which would put us kind of further away from our target location. So if they did decide to go with that value for x, there's some analysis they can do to kind of look back and make sure it makes sense in the context of the problem. So that's it. A little lesson there on optimization and the uses that methods that I've found to be helpful, and a couple things that I've changed along the way. So that's it for my video, and we'll see you next time.